So to model the EMT wave, so we can use something we call as the Helmholtz equations. Okay, the Helmholtz equation you can find in study Q page 483 to 485. It discuss more detail about this, so I will not discuss detail about these equations, but you can see in the book. So this is the equations. Okay, this is basically Laplacian. The Laplacian of E is equal to mu epsilon del square E divided by del T square. Right, so we can see that we have a mu epsilon. So that means we have both the magnetic and electric part. So when we expand more, let's say we only interested to analyze in Cartesian coordinate. Okay, for the Laplacians, so we have the del square E divided by del x square. We have the x, y, and z component. So it's equal to this thing. Right. So to simplify analysis, we have to make assumption, which is the electric field has only one component. For example, we have a EX. Okay, so the direction of propagation is Z. Okay, so this is the example of the expression. The E field is equal to it has only the X component. Okay, or isolate in the X directions, and it function of time and also the propagation direction is Z. Okay, so we can make the equation to be simpler. So this is our expressions. We move to the EY and EZ. So this is our equations. So further detail to solve this equation, this is what you got. Okay, we have the quite the long derivation, so you have to see more detail about this. Maybe you will be asked to derive the equations. Who know? So, but I want to stress about this equation. The solution consists, for example, the electric field here, Ex, it has the Ex plus and Ex minus. And then this function, or in terms of we assume that the wave is sinusoidal. Okay, so in terms of the cosinus, we have the Ex plus cos omega t minus beta z plus Ex minus cos omega t plus beta z. So we have Ex plus and Ex minus. So what is this mean? Okay, this wave propagate in forward or incident wave and backward reflected wave. So we can see that the wave can be further propagate forward, and also it can be reflected. Okay, so from this expression, so we can illustrate into this figure. We have the Ex plus propagate forward, and also we have the Ex minus, which is the backward. Okay, so we have two conditions here. Okay, for magnetic field also, it will be the solution will be almost similar. Okay, this is the solutions. Basically, these two equation, okay, will be used to derive this. This also you have to study yourself. Similarly, for magnetic field, we have the forward wave and the backward wave, right? And then for H, normally we have only one component, which is Y. But it can be different because we have, when we have E in the direction of X, or they only have X components, and we set H to be in the Y h only have y component and propagate or isolate only for y direction, and both wave will propagate in z directions. Okay, so our limit and limit to the focus on the propagating wave in forward direction only. So we consider only the forward direction, so the backward will be ignored. And then another thing is no component of E and H in the direction of propagation. That means our propagation in Z direction. Okay, so we don't have any Z component for E and H. Okay, so Ez and EH is equal to 0. E and H always normal to each other, perpendicular. Direction of propagation is, this is the direction of propagation, AP equal to AE cross AH. So please use this in your solutions. So the direction of E and cross product is direction of X. So we can see that the propagation, the E field and H field has or always perpendicular each others. This is actually the illustration of the electromagnetic wave. It consists of electrical field and magnetic field propagate in the same direction as shown in the figure. Let's say we set E field to be in the x direction. This is x. So you can see that the E field isolate up and down to the x axis, right? And the magnetic field, if here is a y component, so it isolate around the positive y and negative y. So this is a sinusoidal wave. Okay, so you can see that is perpendicular each other, right? And these two wave is always propagate in this direction, with these z directions. Okay, so this is a final expression for E field. Okay, when we consider all the forward directions, so the E component equal to E naught, so this is amplitude, cos omega t minus beta z x. So it has x components, and here something related to the direction of propagation. Here is the direction of propagation, which is z. Okay, we have beta and we have omega. Omega is the radian frequency, and we have time. So this is basically the general equation. So basically E can be in terms of y direction, and it can also be in z direction. So that's mean in our course we only consider that the E and H only have y component, but not necessarily um, x and y. It can be y to z. So we have to see carefully the expression, because here normally z can be changed to x or it can be y. So be careful. So when we further analysis this expression, we can say that the omega t minus beta z is always a constant, and the z is equal to omega over beta t minus a constant. Okay, so the dz over dt is basically omega over b, because we have only t here. Okay, so this is what we call a velocity. Velocity because the distance divided by time. Okay, distance in a cycle divided by time in a cycle. Or we can, or u also can be represented as a lambda divided by t. Lambda is basically the wavelength, t is the period of the wave. Or we can write as a lambda f, because f frequency equal to 1 over period, 1 over time here. Okay, this is a further analysis of this.